Hello everyone, my name is Khashayar, and today in this video I'll be presenting our work called Nonlocality under Computational Assumptions. In my opinion, this is more of a conceptual result, so I'll try to keep the presentation that way as well. So I'd like to start with Bell's theorem. So I think we've all heard about Bell's theorem, and the statement can be interpreted as there are things in quantum mechanics that we cannot explain within the local hidden variable model. And probably the most famous proof of Bell's theorem that we have is the CHSH proof from 1969, which is in a sense an operational proof because it describes an experiment, or a game as we will call it during this presentation, in which we have two parties that are separated and cannot communicate, and if they're sharing a maximally entangled state, they can achieve a score of 2 square root of 2, and if they're within the LHV model, the maximum score that they can achieve is 2. So this is the depiction of the CHSH game, and as you can see we have two parties, A and B, each getting a random bit as an input, X and Y, and outputting A and B, which are again bits. And the winning condition of the game is that A plus B should be equal to X times Y. So there are two main concepts in CHSH that are bound together by this proof in a sense. And the first concept is non-locality. Non-locality in a sense is independent of quantum mechanics, and it's about the probability distribution. And we say this conditional probability distribution is non-local if I cannot write it in a sense as a convex combination of probability distributions on each of the player's side. And on the other hand, there's the concept of entanglement, which is a completely algebraic concept in a sense, because it's about density operators on a tensor space. And somehow I call a state rho entangled if I cannot write it as the convex combination of tensor states, such that rho1 is going to be an operator on H1, and rho2 is going to be an operator in H2. So I can somehow, by abusive notation, call a state also non-local by saying that I call a state non-local if I have a Bell-like game with the probability distribution that I want from it, P, X, Y given A, B, such that that probability distribution is non-local. So an old belief has been that non-locality is in a sense the operational equivalent of entanglement. So is this true or not? That's the question. So for pure states, turns out this is true, so this was proven by Gizan in 1991, but the case of mixed state is a bit different, because in 1989, Werner proved that there exists some entangled states, which we will call Werner states, such that for any Bell-like game that I have, there is a local strategy that simulates the desired outcome distribution exactly. Which means, as soon as I consider mixed states, the statement is not true anymore. So, the original Werner proof only worked when we modeled the players in the games as boxes performing projective measurements, but then this was extended by Barrett to all POVM strategies as well. And then in 2015, Hirsch gave like a more algorithmic approach to constructing these local hidden variable models. So now, if we look at the Werner state, so the Werner state is a maximally entangled state with some white noise, and for all alpha values that are larger than 1/3, the state is going to be entangled. But if you notice, for all alphas less than 0.65, we have local simulations of any projective measurement or POVM strategy that I can have with these states. And only for alpha larger than 1/√2, the CHSH inequality is being violated. So this is kind of unsatisfactory because I wanted this equivalence between non-locality and entanglement, but somehow all the states with alpha larger than 1/3, so in this segment, are entangled, but for a bunch of them, I actually can locally simulate all Bell-like POVMs that I have on them. So the question is, can we fix this mismatch? So a common way to try to fix this mismatch has been trying to redefine what non-locality actually means. So because the non-locality that we talked about was a Bell non-locality. And there have been several works trying to do this. For example, in 2012, Buscemi had this introduced this bell-like game that the classical inputs to the provers were swapped to the players or provers were swapped with quantum states. And then Branchiard et al. Also in 2013 had a different game with 4 players, such that the 2 new players were sharing a maximally entangled state with the 2 main players of the game. And in both these models or definitions of non-locality, it was proven that all entangled states are in fact non-local. So, what do we do in this work? Our approach is kind of similar, but we want to keep some things similar to the original Bell game. So we want to have 2 parties, we want to have classical inputs and outputs, and the main change that we have is that we want the provers or the players to be efficient. So why does this somehow make sense in a physical sense is that if we think of this as an experiment, we don't want to run this experiment forever. And now if we think about the extended quantum Church-Turing thesis, this means that we should be able to model these players as quantum polynomial time algorithms. And also for the soundness part, we will not care about the local hidden variable model cheating strategies that are not quantum polynomial time. So we give this definition of non-locality a name, and we call such states not efficiently local, or NEL for short. So what is the first result that we show? Is that we show that under the assumption that LWE is hard to solve by quantum computers, then all entangled states are actually non-local with this new notion. And we have an operational proof, meaning that we describe a game with 2 players, but the game runs in several rounds instead of us having a single question and a single answer, and the inputs of outputs of each prover are classical. So if we want to state it as a theorem, we have that for all entangled states rho, there exists a game G such that first of all, it's correct. So there exists 2 efficient provers sharing rho that can win the game with overwhelming probability. And it's sound, meaning that under the assumption that LWE is hard, no pair of efficient local hidden variable model provers can succeed the game with significant advantage. Okay, so let's look at the proof idea. We start with the Buscemi game. So the Buscemi game is similar to a Bell game, but as I said, the inputs are swapped with 1-qubit quantum states. And we want to compile this game into a game with classical inputs using some cryptographic tools. And the tool that we will use is a remote state preparation protocol. So in a sense, instead of inputting X to the player, we will interact with the player and make him prepare X by himself, and then do the same thing that he was doing in the Buscemi game. So what happens is that the referee either runs the RSP verifier or runs the Buscemi verifier in each round, and then collects statistics. And the guarantee that we get is that this game would have the exact same guarantees if the RSP is sound. So this brings us to the second result in this paper, which is about the inverse implication. So somehow what we wanted to see was that after proving that hardness of LWE implies that all entangled states are not efficiently local, we wanted to see what the inverse implication is, meaning that what is the minimum computational assumption needed for all entangled states to be not efficiently local. And what we showed was that if all entangled states are non-local in our language, then BQP cannot be equal to PP. So let's take a look at how we prove this. And the main component of the proof is looking deeply into the Hirsch local hidden variable model. So what we show is that the cheating players in Hirsch's LHV model can be implemented in PP. And what I mean by that is that they can be implemented using an oracle that can solve decision problems by post-election. And because of Aronson's 2005 result that post PQP is equal to PP, we get that these strategies can be implemented in PP. Now, to finish the proof, we assume that all entangled states are not efficiently local, so there should exist a game for the Werner states where alpha is between 1/3 and 1/3 and 5/12, which is exactly the range that the Hirsch simulation works. So this would imply that the Hirsch LH3 cheating strategy for G should not be in BQP, because as we said, we assume that all entangled states are not efficiently local. But we've already proven that the Hirsch strategy is in PP, so if we put all this together, we get that this cheating strategy should be in PP but not in BQP, which finishes the proof. So this brings us to the third and last result in this work. And so far we proved that hardness of LWE implies that all entangled states are non-local, and also that if all entangled states are non-local, then BQP is not equal to PP. But the question is, can we combine these results and the things that we've proven along the way to prove some kind of impossibility result for a cryptographic primitive, in a sense? And that's exactly what we do in this last section, and we prove an impossibility result for a certain family of delegation protocols. So let's just quickly go through what a delegation protocol or a classical verification of quantum computation is. So it all goes back to this famous problem that is there a way to classically verify the correct execution of a quantum circuit? And the incredible work of Mahadev in 2018 showed that if we assume LWE is hard, such a protocol exists if we only care about cheating soundness against cheating provers that are in BQP. And the question remaining is that can such a protocol be unconditionally sound? And a work by Aronson and others in 2019 showed that a blind CVQC cannot be unconditionally sound. So what we show in this work is that a one-round CVQC protocol cannot be sound against PP adversaries. And this is done exactly by combining the two ideas that we had for proving the previous theorems. And the nice thing about it is that the proof somehow provides a framework for proving even stronger impossibility results. We'll get back to that later. So let's go through how the proof works somehow. So again, similar to the first result, we build a compiler that takes a semi-quantum game and a PP sound one-round CVQC and outputs a Bell-like game with the same guarantees as long as we only care about cheating strategies that are within PP. Then having this, we can take the Buscemi game again for the Werner states for the range of alpha that the Hirsch simulation works. And if we compile this game with the CVQC, we should get that there should be no pair of PP-bound LH3 players that can win with significant advantage. But then we proved that the Hirsch cheating strategy is in PP, which gives us the contradiction. So such a CVQC should not exist. So now let us conclude this talk. So what did we do so far? We introduced a new computational notion of non-locality called NEL. Then we proved that under the assumption that LWE is hard, all entangled states are non-local in this sense. And we proved that the minimal assumption, so a lower bound assumptions that we have for all entangled states to be not efficiently local is that BQP should not be equal to PP. We also introduced a new framework for proving impossibilities for delegation of quantum computation, and we proved that a single round delegation protocol cannot be PP sound. So what are some future work directions that can be pursued? The first one is an operational certification for all entangled states that does not use the quantum mechanic toolkit. So this is true for CHSH, for instance, but not true in our case because we explicitly need to model the players that we have as POVM, as doing POVM measurements. But for instance, if there is a way to do this with a non-cloning argument or things like that, then this might be possible. And the second interesting direction, I think, is seeing what does all entangled state being non-local actually imply more than the fact that BQP cannot be equal to PP. So for instance, can we actually build a cryptographic primitive out of this and not just a complexity class separation? And the third one that I talked about shortly before is proving stronger impossibility results. So there are two ways that I think can be this can be done. First is tightening the soundness guarantee. So instead of having impossibility for PP sound provers, for instance, we can have against some even weaker prover. And this can be done by getting a better class separation implied by all entangled states being non-local. And the second one is the fact that we only prove impossibility for a single round delegation protocol, but this is not really a limitation of the proof, but the limitation of the local hidden variables, because local hidden variable models for many round games have not really been studied. So this might be a good motivation to study such local hidden variable models. So that's it. Thank you for watching. And if you're interested in learning more, here's the link to the paper. Thank you.